Imagine you are one of 100 prisoners. The prison warden offers the 100 prisoners sentenced to death one last chance. The prisoners are numbered from 1 to 100. This is the most interesting and at the same time the most astonishing problem in the field of combinatorics, logic and large numbers. It astounds everyone who encounters it for the first time, understands and grasps the essence of the problem. The problem of the 100 prisoners and boxes was first considered in 2003 by Danish computer scientist Peter Miltersen, who published it together with Anna Gall in the report of the 30th International Colloquium on Automata Languages and Programming, IKLP. In their version, player A, the prison warden, randomly colors strips of paper with the names of Team B players, the prisoners in red or blue, and places each strip in a separate box. Some of the boxes may be empty. For Team B to win, each of its members must correctly name their color after opening half of the boxes. In the form of the 100 prisoners and boxes problem, it was posed in 2006 by Christoph Papp in the journal Spektrum der Wissenschaft. This is a textual description of the problem's conditions. You can view it by pausing this video and thank you. Then we will proceed to analyze the problem. The warden randomly places in each box one of the numbers from 1 to 100. All boxes have different numbers. The essence of the problem is that each of the 100 prisoners must find their number in one of the 100 boxes for all of them to survive. If at least one fails, they will all die. Each prisoner may open only 50 boxes and cannot communicate with other prisoners except for the preliminary discussion of the strategy. Let me tell you what will happen if each prisoner entering the room opens the boxes randomly, trying to find their number. In this case, considering that they can open 50 out of 100 boxes, their chances are 50 out of 100, meaning 1/2, 1 to 2, or more precisely, 50%. Either they find it or they don't. But on a large scale, there's a huge failure here. Since if the chance of one prisoner randomly looking for their number is 50%, which is 1/2, then for all 100 prisoners to successfully find their numbers is almost fantastical. After all, if one person has a 1 in 2 chance, then for 100 it would be 1/2. We have 1/2, we have 1/2, and so 100 times. That is 1/2 to the power of 100. And that equals 0.000000, and so on for 30 zeros after the decimal point and 8%. Well, that's the insignificant value we end up with. It's more incredible than a blind cat painting the Mona Lisa with precision to every thread. Even that would sound more plausible than 100 prisoners who by randomly opening boxes all found their numbers. Mathematics often surprises. This is called exponential growth, but just the opposite. Our chances decrease and the inverse chances grow. The chances that nothing will work for us. Yet this is not a sentence. Knowledge of mathematics will help us here too. It seems absurd and involuntarily raises the question, but how? The answer is in the so-called chain strategy. After all, initially we are given a chance to discuss the action plan once. So what's this strategy plan about? Then let me lay it out. We use a strategy called the chain strategy. Each prisoner enters and first opens the box with the number corresponding to their own number. In our case, we see how the prisoner with number 1 enters and opens the box with the same number. There he finds a paper. Then he opens the box with the number indicated on the paper from the previous box, and so on, following the chain. This chain will eventually lead him back to his own number if the chain does not exceed 50 boxes. This strategy offers a much higher chance of success compared to a completely random selection of boxes. The so-called chain strategy increases the chance of success only up to 31%, which is a significant increase. Just imagine from this to that. It is the same as increasing the size of a fly to the size of the observable universe. Why is that? Because the probability of encountering sequences longer than 50 is 69%, while the probability of encountering sequences no longer than 50 is 31%. For example, the probability of a chain exactly 100 units long is only 1%. If we add the probabilities for all chains from 51 to 100 units long, we get a total of approximately 0.69 or 69%. Therefore, the remaining 31% is the chance that all chains will be no longer than 50 units. And this is the condition for victory. Thus, on average, in roughly 1 out of every 3 cases, or 1/3, the experiment concludes successfully. If we conduct such an experiment 10,000 times, we will probably get a result where approximately 2,900 times all the prisoners were able to find their numbers written on papers, which were hidden in boxes. For this, I even wrote my own program in Python. It fully simulates the complete functionality of the original problem. The experiment turned out to be quite interesting, I would even say thrilling. Below you can see the graph with the chain strategy. It has a quite interesting appearance. On the right you can see the case when all 100 prisoners found their numbers. It stands out and it is probably around 30% of the total amount. And this is a graph of random selection when prisoners opened boxes without relying on any strategy, just randomly and haphazardly. You can see many mathematical wonders here too. It's like with a golden board, the values are evenly distributed in the middle. Now it seems like we will get these values no matter how many times we repeat the experiment. And this is a clear comparison of the two graphs. It's true what they say, the universe speaks the language of mathematics. Here, it seems to me, lies some invisible, profound meaning beyond the reach of the human mind.